Welcome everybody. So now we're going to start a new chapter now on ordinals. Before we did cardinals and ordinals, they sound similar, but they are a different thing. They're related. And before going into ordinals themselves, we're going to go into well orderings, which is kind of the base for ordinals. Okay, and before going to well orderings, let's review some basic definitions. First, a partial ordering is a structure with domain some set and a relation on it. So this is a binary relation, so that means it takes two elements and tells you whether the relation holds or not of those two elements. And the relation must be transitive and irreflexive. So let's review what those are. So transitive means that if you have x, y, and z, and you have that x less than y and y less than z, then x less than z, right? So that's transitive. Irreflexive means that for every x, x is not strictly below x. Yeah, so something that satisfies those two properties is called a partial ordering. Oh, one thing to comment here is that whenever you have a partial ordering, you can define a relation like less than or equal as x less than y or x equals y, right? So we'll use that a lot whenever you use. And sometimes partial orderings are defined using this as the basic notion, the less than or equal as the basic notion. And in this case, you gotta require that this relation is transitive, reflexive, and antisymmetric, and then you define the strict notion from it. So yeah, you could go either way, defining one or the other. I guess depends on what you're working on. Some is easier, but usually one defines it one way, but then uses both notations, this one and that one. Okay, examples. Let's see a couple of examples. You guys know a lot of examples. So for instance, if you take the power set of any set, and as the binary relation, you take inclusion. Inclusion is transitive, right? If A is including B, B is including C, then A is including C. Oh, that's not good because every set is including itself. So we need to take a proper inclusion. Proper inclusion means you're included but not you're equal. And that's if you want this proper definition, proper ordering, you'll get that. What about power set of A together with the belongs relation? Well, no, that's not a partial ordering because you may have A belong to B, B belong to C, but A doesn't belong to C, right? Unless the set C is transitive. No, we don't get that. That's not a partial ordering. Another one, we can take the natural numbers with the divisor relation. Let's call it like this, where the relation that holds of two elements if the first one divides the second one, or if the second one is a multiple of the first one. So that's a partial ordering, right? So you have, in this case, you have 2 divides 6, 3 divides 6, 2 does not divide 3, 3 does not divide 2. It's a partial ordering. Cool, and so that's it. So an ordering is a partial ordering is an ordering of elements where not all elements need to be related. Like in this case, 2 and 3 are not related. And also in the case of inclusion, we may have subsets of A which are not subsets of each other. When you want that to happen, or when that happens, what you have is a linear ordering. In a linear ordering, you have that for every two elements, they have to be related. Either they are equal, or x is below y, or y is below x. So they are called linear ordering because they have to be ordered kind of in a line, right? So the natural numbers, let's say, or the integers with a usual less than or equal, that's a linear ordering, or the reals with the usual less than or equal, so linear ordering. They look like a line. You can have more complicated linear orderings. You can have like a copy of the integers less than or equal, and then when that's done, you take another copy of the integers and you put it right here, and you get a new linear ordering that we call z plus z, and it's longer than it's just two z chains, one after the other. That's the linear ordering that satisfies the properties. Okay, so those are linear orderings. What we're going to be discussing is a particular case of linear ordering, particular class of linear orderings, and they are called well orderings. So they are, I guess, better than linear orderings in some sense. So a well ordering on a domain A is a linear ordering with the property that every subset has a least element. Okay, every subset has a least element. So what are the examples of things like that we know? Well, we know the natural numbers with the usual ordering. That's the standard property of the natural numbers, that every subset has a least element, right? While if you take, for instance, the integers with the usual ordering, that's not the case, right? If you take, say, the negative integers, there is no least among all the negative integers. Like you go to minus infinity, there is no least one, right? Do we know other examples? What if we take something like we did before? We do n plus n. This is an operation of linear orderings. This one looks like copy of the natural numbers, and when that ends, we put another copy of the natural numbers. And essentially we say all the ones on the right copy are larger than all the ones in the left copy, and then among themselves they order in the right ordering. Yeah? So the domain of these is kind of the disjoint union of two copies of the natural numbers, and the order is defined, the ones in the first copy are larger than the ones in the second copy. Or the other way around, yeah. In this one, every subset has a least element, right? Because if you have a subset that contains some of the first copy, it's going to have a least element there. If you have a subset that is only in this part, it's going to have a least element in there. So that one is a well ordering. We're going to be talking more about this guy later. We can do, for instance, n cross n with the lexicographic ordering, where n m is less than a b. If you first look at the first coordinate and compare just the first coordinate, if n is less than a, or n is equal to a, and in that case when they are equal, you look at the second coordinate. Okay, this is kind of like lexicographic ordering, right? You first look at the first coordinate, n and a, compare those. If you get a comparison, that's it. If those are equal, then you look at the second coordinate. So that's an ordering, and that is a well ordering in the natural number in that n cross n. Why is that? Let's prove that. So to prove that it's a well ordering, we have to take a subset of the whole set, and we gotta show that it has a least element. So what is gonna be the least element? So first, just look at the first coordinate. So let B0 be the projection of B into the first coordinate, the set of all n's such that there exists an m such that n comma m belongs to B, right? Just the projections on the first coordinate. And so this is a subset of the natural numbers, right? So it has the least element. Let's call it B0, all right? So now, among all the elements that are in B, they all start either with B0 or they start with a larger element. Because among all the possible first coordinates, B0 is the least one, right? And now we have to look at the second coordinates. Now let B1 be the set of all m's in the natural numbers such that B0 comma m belongs to B. Right, so this set B may have many elements that have first coordinate B0. Those are going to be the smallest one, right? Because if you have a larger first coordinate, you're bigger. So look at the ones that have first coordinate B0. Consider those sets. That has the least element because it's a subset of the natural numbers. Let's call it B1. Yeah, so now what do we get to finish? Well, we get that the pair B0, B1 is the list of B. Great, so we started with a subset B of n cross n, and we found the least element, first by looking at the first coordinate and then at the second coordinate. Cool. Let me tell you about another example. I let you guys think about this one. So consider the set of polynomials with natural number coefficients. Okay, this is a polynomial with natural number coefficients, and ordered by this relation, where we have a polynomial, we define it to be less than another. The limit as x goes to plus infinity of qx minus p of x is greater than 0. Okay, so it's an interesting definition. I let you guys think about this one. I claim that, well, even showing that this is a linear ordering is not immediate. But yeah, it's actually even a well ordering. Yeah, you guys think about it. Okay, so we have a bunch of examples of well orderings. Well, essentially we have not that many. We have the natural numbers plus the natural numbers, the natural numbers times the natural numbers, and these polynomials, and actually there are many more. Of course, if you have a subset of a sublinear ordering of a well ordering, if you restrict it to a smaller set, you still have the property that every subset has a least element, because a subset of a subset is still a subset. So, and here we get kind of like the natural numbers are smaller n plus n. They're getting a larger in terms of well orderings in here. Here's another property that will help us visualize more this property of being a well ordering. So this theorem says that being a well ordering is exactly equivalent to the following. It's exactly equivalent to containing no infinite descending chains. Okay, so let's put an infinite descending chain. What is an infinite descending chain? On a linear ordering is a sequence A0 greater than A1 greater than A2 greater than A3 greater than A4 greater than A5 ... all the way to infinity. Okay, so I guess formally you would say it's a function from the natural numbers to A such that A n is greater than A n plus 1 for all n. Yeah, so that's a decreasing sequence, the sequence that goes down. And we're claiming that being a well ordering is the same as having no such descending sequences. So let's see why this is the case. Let's prove this one first. Suppose towards a contradiction that B subset of A has no least element. Now define a sequence as follows. So let B0 be a member of B. Of course, you need here, when we say every subset has a least element, of course we mean every non-empty subset has a least element. Empty subsets, yes, I guess have no least elements. So non-empty. That's what you need for the definition of well ordering. So there must be some element inside. And now we're going to define a chain. B0 is not the least element, so there is a smaller element of B that is inside. B0 is not the least element of B, so there is another element B1 in B that is below it. B has no least element, so B1 is not the least one, so there must be a smallest element in B. That's not the least one, so there must be a smallest element in B. It's not the least one, so there must be a smallest element in B. And we continue like that. And since there are no least elements, we always are able to find another element below, right? So that's how we build our descending chain. If from an element with from a set with no least element, we stay inside the set and we keep on going down. To define this formally, you need to apply, define this sequence by recursion of the natural numbers, right? So you're defining each value using the previous one, and you need to use the choice axiom to pick some element below each one. So I'll let you guys work out the details for that. For the other direction, suppose now that we have a descending sequence, and now we want to show that there is a set with no least elements. So what is that set? Okay, so we just take all these guys, the set of all these guys. We put them all in a set. That set has no least elements, right? Because each of these guys, Bn, has a smaller element, Bn plus 1, and a smaller one has no smaller element, has no least element. Okay, so those two things are equivalent. No infinite descending sequences, and and every set has a least element. So those are well ordered for you. Let's prove a few properties about them.